ideas of what their result was, and then anyone who wants to ask questions can do so. There's the Slack channel where you could type a question. There's the chat channel you could type a question, or you could just attempt asking a question if it doesn't get too out of control. Also, the speaker can certainly share their screen if they have any slides for those 2 minutes or in order to answer any questions. Any questions about the format? No? Okay, then I'll let Frank begin. His talk is on kinetic geodesic Voronoi diagrams in a simple polygon.
Yes, thanks. Let me maybe just share my screen, not so that you can just look at the picture. That's easier to explain. Right. So the basic problem is this of geodesic Voronoi diagrams. Right. So I have some sort of a static, simple polygon with a bunch of sites, so points inside there, and we want to maintain a Voronoi diagram, so a partition of the polygon into regions, such that every site has a region, and all of the points in this region are closer to that particular site than anywhere else. Right. So here's a example with our co-authors and who some sort of a description who was supposedly closer. And now the thing is, like, can we maintain this diagram? So somehow this purple curve that partition the polygon into pieces if the sites are moving, right? And so let me very quickly scroll down to an example that is maybe slightly more interesting. Right, so here's a maybe more complicated figure. And so if you can sort of imagine that if these sites are moving like the blue guy, then somehow these purple curves, they're also moving and changing. And in particular, the structure can change. And there will be, like, if this blue guy is moving upwards, then this purple curve will also sort of move upwards, right? So these points over here, they will get closer to this blue point. And so there will be these structural changes in the diagram. And the question is, okay, so when do these happen? So how often can this happen? And can we somehow maintain this type of structure? And as you can also sort of see in the background here is that, like, there's also these other, these sort of pink-ish vertices that somehow where the structure or the bisectors change. And they, they essentially also cause these changes. And so the number of these pink vertices, that somehow depends on the complexity of the polygon rather than on the complexity of rather than on the number of moving sites that we have. And so I guess our main contribution is to show what this dependency on the boundary of the polygon is. And so what we do show is that, like, even if I have a single bisector, so even if I just have 2 points that are somehow moving, then you can already get a cubic number of changes, cubic in the complexity of the polygon. And we show that we can actually maintain this bisector somehow efficiently. And so this, like the important thing is that this bound is tight, right? If I have 3 sites, then you can talk about a single Voronoi center, so a point that is equidistant to all of these 3 sites. And there we see the same thing, that like you can get a cubic number of changes in sort of how this point is moving as a function of how the original 3 points are moving. And using those results, then we also managed to give bounds on the number of changes in a Voronoi diagram of n of such sites. And there we have something like a n cubed, m cubed upper bound. This time this is not tight, but there's a much weaker lower bound. Which is also, again, it's like cubic in the number of corners of the polygon, but only quadratic in the number of sites, essentially. So there's still a gap. And then we show how you can maintain this diagram, somewhat efficiently. It processes these very many events somehow, or at most this many events, and somehow it processes them more or less efficiently, I would say, where more or less it depends on how many neighbors a single Voronoi region can have. mean, ideally we would get rid of this K factor, but again, that seems pretty tricky. And I guess that's like, yeah, I mean, I don't really want to say much more about the problems itself, because like how we do this, yeah, I mean, I can't really explain it in 30 seconds. So I guess I'll just keep it at that.
Yeah, and again, these 2-minute talks are just meant to remind people in the hopes that they've seen the videos already. So any questions? Okay, I have one. Is that in these diagrams, there's a lot of sort of degree 2 points going on there. By combinatorial changes, you're really talking about the combinatorial changes, including all these degree 2 points. What if you contracted them and you just wanted to maintain the overall tree, the shape of the tree, without worrying about all of the degree 2 points in there? Would that make life easier?
Yeah, so we did think about this. I mean, I can't remember if we explicitly gave a bound on the number of those changes. I mean, so one thing is, of course, that like even though you might not be interested in all of those degree 2 vertices themselves, I mean, I guess you are interested in when a degree 3 vertex, so one of these purple guys, when it bumps into its neighboring degree 2 vertex, because that means that you do get some sort of a change in how this guy is moving, and like even with those changes, you can get a large number or a large fraction of those changes. The other part is, I guess, that in our kinetic data structure, this is more or less what we're doing. So we have some sort of efficient data structure that somehow stores all of these degree 2 vertices on a bisector, and well, it handles them efficiently, like without explicitly having to look at every single vertex somehow. So yeah, I mean, it's definitely something to think maybe more about if we really only care about this structure, then if there is something better that we can do than what we currently do. Also, it's not actually a tree, right? So in general, this it can be an arbitrary graph structure.
Yes, for sure. Any other questions for Frank?
I would have a very simple question, maybe. So just out of curiosity, is there like a simple case of this problem? So if I make the shape easier, does it get trivial at some point, or very easy, or much faster? I mean, the lower bound also has kind of like a complicated shape, like all around. But if the polygon is convex or something, or
yeah, I mean, so if the polygon is convex, then basically we're in just the Euclidean setting, right? Then it doesn't really matter that there's a polygon, because all of the distances are just the Euclidean distance. Okay. And so actually, so even there, like this is kind of an interesting and somewhat infamous problem, because so there's like this n-cubed upper bound on the number of combinatorial changes. And for very long, like the best lower bound that we have is quadratic, and so for very long this was really wide open, and only a few years ago there was this near quadratic upper bound for the case where all of the sites are moving with unit speed, right, with the same speed, and then there's this like slightly subcubic or subquadratic, super quadratic upper bound, but yeah, even in the setting where somehow the sites have different speeds, then the best upper bound that we have is still cubic. So yeah.
Okay. Thanks.
Okay, thank you. Any other quick questions? We have 1 minute.
Yes, I have a question. So can you interpolate between these two cases maybe? So if you let's say you analyze this in terms of the number of reflex vertices, and you replace number m?
Yeah, so I'm guessing that most of our m factors, they more or less directly can be replaced by a number of reflex vertices. but I haven't gone through the math itself. I would think that you can more or less directly replace the n's by r's or something like this.
Okay, thank you very much. Let's move on to the next talk, which is on scattering and sparse partitions and their applications by Arnold Pilzer of Columbia University. Arnold, if you want to share whatever you want on the screen and begin a short overview. Thank you.
So, hi, thank you for the introduction. Let me remind you or introduce you to the talk. So the main problem we were studying is the standard polynomial problem. Here we are given some weighted graph G, and the goal is to reduce the graph or approximate it with a minor. So in a sense, you want a smaller graph that will preserve both the geometry and the topology in the graph, in the following sense, that you want that every pairwise distance will be preserved up to some approximation factor alpha, and that the new graph M will be a minor of G. And the question is, what is the best distortion possible? So the best for general graphs is log k, where k is the number of terminals, kind of the set of vertices you want to preserve here. And the best lower bound is 8, so there's quite a gap. And the main question we ask is, what about some special graph families, where actually the gaps is the same? The main part of the paper, we're studying some partitions. So first we studied this sparse partition scheme, where it in a sense is a clustering of the graph. And there are 3 parameters, sigma, tau, and delta. So you want every cluster to be of diameter at most delta. And we want that every pole of radius delta over sigma will intersect at most tau clusters. So this type of partition was previously introduced. There's like partition scheme if you can do it for every parameter delta. And J et al. Showed that if you can construct such a partition scheme with parameter sigma tau, this will imply solution to the universal Steiner tree problem with distortion polynomial in tau and sigma square. So I don't have the time now to define what this problem is, but it's quite interesting. So in this paper, we defined quite similar partitions, which we called scattering partitions. And here it's essentially the same, where instead of balls, we care about shortest paths. And we want that every shortest path will intersect every shortest path of length at most delta over sigma will intersect most tau clusters. Like here, this path intersects 3 clusters, this one 2, and so on. And you can get a partition scheme if you can do it for every parameter delta of diameter. And yes, the first main contribution of the paper is the following theorem that states that if you can construct such partitions for every induced subgraph with parameters sigma and tau, this will imply a solution to the standard polynomial problem with distortion polynomial in tau and sigma. So now, in a sense, it gives you like a way to construct good solutions to the problem. Just construct such solutions. And let me just say that in the previous type of partitions, the sparse partitions, there are kind of 2 types, with strong and weak according to the diameter guarantee. And specifically, what J et al. Needed this weak sparse partition. And the main part of the paper is just constructing different type of such partitions. So in a sense, we have this picture here, where in a sense, we see that every strong sparse partition is also scattering and weak, while weak and scattering is kind of not always coincide. Then we partition many graph families into different partitions, getting some new results for standard polynomial removal and universal Steiner tree problems, also universal TSP. And we also left some interesting open questions. I guess the main open question is about planar graph. So actually, the bounds about the standard removal problem for planar graph are the same as for general graphs. It is 8 and log k. So here, if you will get a partition with a constant, it will imply constant distortion for the standard removal, which is believed to be true. And so currently, we don't know. We only know how to construct weak sparse partition for this type of graph. So the same question is also valid for 3 with k graphs, where we again know how to construct weak sparse partitions, but not scattering. And final question is about general graphs, where we know how to construct log and strong sparse partitions, which is tight, but this is the same parameter for scattering partitions, but there's no lower bound, and I believe it to be a constant log n. So.
Okay, thank you very much. Are there any questions? Questions?
I guess it was very clear.
So I understand that if you have such a partition, you automatically get an efficient solution for the Steiner tree removal
So
problem.
it's actually not a single partition. You need like a scheme.
Okay. Yes, that's what I meant. But how efficient is this? Like, is this? Is this a fast algorithm, or is this just like a polynomial?
Oh, is this no? I guess it's just polynomial. It didn't really compute the running time.
Oh, okay.
Yeah. It's more of existential type of problem.
Okay,
you know?
okay.
I mean, before you want to do it fast, you actually want to know that you can do it. And
of course,
I mean,
of course.
Yeah.
But there is an algorithm like that.
Right. There is an algorithm, it's polynomial algorithm.
Okay.
Yeah. So actually, I mean, for example, the best algorithm for general graphs could be run in almost linear time. Yeah, but it's just an artifact of it being very nice and natural algorithm, not of me trying very hard to do it.
Thanks.
For a lot of these decompositions, they're useful at one level, but also they're useful in a recursive sense. Is that the case here as well?
Yes. So in a sense, if the way you construct the minor is by like creating this partition for like some large scale, doing some partition, it's some small scale, doing some partition, and then like continue partitioning the supergraph. And then you construct them kind of in a recursive way. Yeah, so in a sense, in the universal Steiner tree, this is also what they do. And this is, by the way, the reason that the tree they get is not a spinning tree. It's like it's another question about like similar problem, if you remember from my previous talk. What is the universal Steiner tree problem? So in a sense, the goal there is to construct a single tree that approximates all the Steiner trees of all possible terminal sets. And what they show that you can do it like with stretch about log square. But if you wanted the tree to be a spanning tree, then it's like best upper bound known is about like 2 to the root of log n. So, well, it should be polylogarithmic, at least believable to be. And the main barrier is to construct such partitions in a recursive manner. In a sense, we know how to construct single partition, but if you want a hierarchy of strong sparse partitions, it's open.
Any other questions? No? Okay, well, thank you very much. Let's move on to the third talk, which is extending partial one-planar drawings. And Delka is giving the talk, and the majority of the authors are from the Technical University of Vienna in Austria.
Yes, 1 second. Okay, I hope you can all see my screen. Can you hear me?
Yes.
Okay, good. Okay, so let me just quickly recall the problem. So what we looked at was a drawing extension problem, which means that we are given a graph G that we want to draw, and part of it, namely a connected subgraph, is already drawn. So the task is to somehow extend the partial given drawing to include all edges and vertices of G. And as is usual in graph drawing problems, we are not really interested in getting arbitrary drawings, but drawings that have some desirable properties. So of course, we're not the first people to study such drawing extension problems. In particular, previous work includes work on the drawing extension problem where you want the resulting drawing to be planar. But what we looked at is arguably one of the most important generalizations of planar drawings, namely one planar drawings where each edge can cross at most one time. So it is known that deciding whether a graph is one planar or not is NP-complete, and the NP hardness very easily carries over to the one planar extension problem. You can just use the empty drawing as initial partial drawing, and then of course a graph G is one planar if and only if you can insert a one planar drawing of G into this initial empty drawing. But this hardness reduction, of course, heavily relies on the fact that H can contain little to no information about G. So what we asked is, what can we say if G is not too far from H? And formally, the way we did this is to look at the problem through the magnifying glass of parametrized complexity theory. And the parameters we use are based on the deletion distance from G to H, which is, of course, a very natural way to measure how far H and G are apart. So more specifically, we looked at the edge deletion distance. How many edges do you need to remove from G to arrive at H? And potentially some isolated vertices. And we also looked at the vertex plus edge deletion distance, where you are also allowed to remove vertices with all incident edges. This is a list of our results in this work. So our main result is an FPT algorithm parameterized by the edge deletion distance. For the less restrictive parameterization of vertex plus edge deletion distance, we were not able to get the analog result, but we did get something like that if we restrict the drawings we want to end up with even further, namely to IC planar drawings. And we also made a first step in the direction of showing that the problem is at least XP. And actually we managed to get an XP algorithm parameterized by the vertex plus edge deletion distance. This is very recent work which will be published at MFCS. And the main remaining open question is whether or not one planar drawing extension is FPT parameterized by the vertex plus edge deletion distance from H to G.
Thank you. Are there any questions? I can ask, so this is all focused on one planar drawings. Is there any hope of having it FPT in 2, 3, 4, 5, 6 planar drawings as well?
I believe so, at least. So at least for the edge deletion distance, we've discussed this a tiny bit, and we think our techniques carry over for that.
Thank you. Are there any other questions?
Yeah, in your talk, you mentioned lots of other NP-hard generalizations of drawing planar graphs.
Mm-hmm.
Are they similarly interesting? Or will you also be studying whether they are FPT and so on?
So they are also interesting, definitely, but a lot of them would require very different approaches, which is, of course, not a reason not to study them. But yes, they are, of course, interesting.
Any further questions? Okay, if not, we'll move on to the next talk, which is Fréchet distance for uncertain curves. And Alexander Popov is going to be talking, and this paper is from a variety of people in Eindhoven, Utrecht, and in Texas as well. Okay, so whenever you're ready.
Yeah. Let's hope this works. Can you see the slides?
Yep.
Okay. Yeah, so indeed the talk was about Fréchet distance for uncertain curves, just so everyone's on the same page as to what it was about. I mean, Fréchet distance is a distance on curves which is often described with this analogy of a man walking his dog, and then they're walking along their separate curves and they cannot go back. And then the Fréchet distance is the shortest length of the leash that you would need to walk along the entire curves. So that's the example on the right. And then the discrete Fréchet distance is the version where you restrict your attention to the vertices of the curve. So you jump from vertex to vertex. That's the example on the left. And then the other part of the title is about, well, uncertain trajectories. So what does that mean? Normally, when you're talking about trajectories, you would probably represent them as polygonal curves. To model measurement uncertainty, we replace the vertices with uncertainty regions, and we say, well, the object could have been anywhere inside this uncertainty regions. And we distinguish between two models for, well, the discrete one, basically, which is on the left, and the continuous one, which is on the right. And then in each of those, I mean, the true location on the left is one of the L options. The true location on the right is somewhere inside this region. And in terms of our result, I mean, here on the slide, everything in red is what we discuss in the paper and also in the talk. We looked at the lower bound, upper bound, and expected distances. This means, well, we look at a combination of, let's say, discrete Fréchet distance and imprecise model. And then, well, lower bound would be you take the best possible real curves according that comply with your model and say what the Fréchet distance is. The upper bound then is the worst possible curves, and the expected case means you assign some kind of a distribution to your uncertainty regions, let's say uniform distribution, and then you talk about the expected value of the distance. So we show a whole bunch of hardness results for the lower bound Fréchet distance. In one of the settings, we show a dynamic program, and in another setting, we again have a hardness result. For the indecisive settings, we have algorithms for restricted cases where we restrict this matching, and so how you can move along the curves. And for the lower bound continuous case, we have two approximation algorithms. That summarizes the results.
Thank you. Are there any questions?
Is there an intuitive explanation for why computing the upper bound is so much higher, more difficult than computing the lower bound? I mean,
there kind of is, but it's kind of difficult to think about this. So for the, yeah, so this basically has to do with the fact that, well, Fréchet distance is this bottleneck measure, and then for the lower bound, I mean, you can often just sort of look at the possible regions that you have now, and then you don't have to sort of remember what choices you made in the past in terms of realizations.
that makes sense.
But for the upper bound, it's not, doesn't really work out like that.
Thank you. Any other questions?
Two questions in Slack.
Yes, I'm also here. So I
Oh,
can
can
just,
also-
yeah, I can just ask him here, I guess. So you gave a very nice application for the imprecise points in the video. Is there also, I mean, with GPS measurements, and because they're imprecise, so you have a certain region, is there also some motivation like that for the indecisive version?
Yeah, that one's a little bit less obvious, let's say. So there are a couple of things you could think of. One is that, well, maybe, again, with GPS, you have a precise, more or less precise location. But if you're in some kind of a densely built environment with lots of walls, then the signal might reflect from some of them. And then you would have to choose between, well, where you really were and maybe where the signal was reflected from, or something like this. Another thing you could think of, which is quite different, is if you have some kind of a sampling scenario. So you don't really know a distribution for your uncertainty model, but you would somehow be able to sample a bunch of locations and then use that as proxy. But indeed, it's sort of less natural for straightforward applications.
I mean, it's very natural, like, to consider it also in this setting. I just thought maybe you have, also other ideas. I have a second question, but maybe someone else wants to ask before me.
Does anyone else have a question, or? Okay, go ahead, Andre.
Frank just unmuted himself, but okay, let me make it quick. Did you also consider dynamic time warping or some continuous version of it by any chance? I think it's probably harder because it's not a bottleneck measure.
Yeah, we didn't really look at it. I mean, also Fréchet distance is kind of a natural distance for curves, especially the continuous version, in a way, probably more natural than dynamic time warping. But we didn't really look at dynamic time warping, so I'm not really sure what would get there.
Thanks.
Okay, Frank, did you have a question?
Yeah, so do you know if any of these results, if they're applicable to some sort of probabilistic model in which the vertices are there with certain probability and not at all otherwise?
We didn't look at that model, and yeah, I'm not really sure if there's any kind of a straightforward extension from, well, in terms of the techniques that we used. That's something that would require a more careful look, I think.
Okay. Anything else?
I would have a question. So for Fréchet distance, there is this well-known algorithm on CPEC curves. Do any of your results hold for CPEC curves? Or that's open?
Yeah, that's something I don't really know that much about. So that's a bit difficult for me to answer.
Okay. Okay, thank you very much then. We'll move on to our next talk, which is also on curves. We have approximate nearest neighbor for curves, simple, efficient, and deterministic. And Umrit Filzer from SUNY Stony Brook will be giving the talk. So whenever you're ready.
Okay, can you hear me?
Yep, can hear you.
I will show my screen. Okay, so My talk is about nearest curve problem. So you're given a large data set of curves, and you have some distance measure for curves, delta, and you want to pre-process this data set such that given a query Q, you can quickly return the nearest neighbor, the closest curve to Q. So in this paper, we consider the approximate decision version of this problem. So we were also given parameters epsilon and r, and given a query Q, if there exists a curve in the data set within distance at most r from Q, then you want to return maybe another curve within distance at most 1 plus epsilon r from Q. So the distance measures that we consider are all around this curve alignments. So I will not really explain, but you can see what it means from this short animation. And specifically, we consider it can be general, but we consider two main distance measures. So if we minimize over all the alignments the maximum distance, we get the discrete Fréchet distance, as Alexander described earlier. And if we minimize the sum of distances, we get a dynamic time opening. And both these distances can be computed in quadratic time by a dynamic programming algorithm. For the nearest curve problem, for the approximate near neighbor for curves, when we are given a data set of n curves, each with m points in d dimensions, there are basically two extreme approaches for solution. So we can just store the set C without any pre-processing, and the query algorithm will just do all the work and compute all the distances in a huge query time. The other extreme approach is to store the answers to a discretization of all possible queries, EF queries, and the query algorithm will just return the pre-computed answer in linear time. But then we should get a huge space bound. So let's look at the previous work for this. So you can see that there's a constant approximation, but the space bound is exponential in the size of the universe, the domain in which the curves are defined. And other algorithms give query time which is exponential. So what we did is basically we show that if you do the second extreme approach, which is a discretization of all the queries, so you actually get better bounds both in the query and the space. So in the query, we do get the linear query time. And in the space, we also managed to improve the space bound over the previous results. So we do this for both the discrete Fréchet distance and the dynamic time open. And two open questions before I finish is that can we compute a lower bound? Can we find a lower bound for this problem, the neighbor for curves? And the second question is maybe we can find a data structure with polynomial space at the cost of a constant approximation instead of this 1 plus epsilon approximation. Okay.
Okay, thank you very much. I open the floor if there are any questions.
So I again posted questions on Slack, but I guess I'll ask them here directly. So first, regarding the second open problem that you left, do you have any, exactly, the constant approximation with polynomial space. Do you have any feeling how this can be approached, how this can be obtained?
Yeah, it's a good question. Actually, no, we don't have any idea how to make it work, especially because all the other algorithms, all the other methods that will apply for this give exponential bounds. So maybe I'm going to say
something to say. So, I mean, in the kind of similar question of eddy distance, there was some progress And specifically, they even showed, like, I think, almost linear time cost approximation. But I mean, the difference, in a sense, is that in any distance, you can allow yourself to do many mistakes. You're still fine. Well, in Fréchet distance, because it's a maximum, you cannot do any mistake. And this makes kind of much harder to do anything which is like really linear in a sense. So, yeah. It might be possible. We don't know how.
Okay, yeah, yeah. I feel the same. Thanks.
Any other questions?
I mean, so maybe one question. So in your talk, you sort of have as a hypothesis that your space bound is close to optimal. Any reason why you believe that?
Yeah, so actually, by personal communication with the authors of, okay, no, it's not here, Emils and Drimel. So they have a paper showing some lower bound for the for a distance circle for the under the discrete Fréchet distance. So they showed that a distance circle for a distance circle with maybe I'm not stating this exactly what they show, but basically they show that for a distance circle for one curve, you have to have a space bound something like this, order of 1/epsilon to the MD, if you want the query time to be linear like this. So here because it's the nearest curve problem, we have this additional n. So this is the reason why.
Okay. Anyone else want to ask a question?
I would have another one if no one else. And so extending this to the continuous Fréchet distance would be interesting, but I also guess that it gets like the techniques don't really carry over.
Right, they don't carry over because I mean you can have a long edge, and then if you want to discretize all the points near this edge, you get, and the number will depend on the length of the edge. So yes, you need, I guess you need a different approach.
Okay.
And just to clarify, the pre-processing time or the time to build the data structure, that's proportional to the space, I guess?
Yeah, yes, more or less, maybe a logarithmic factor or something like this. But yes, it's quite the same.
This rotation, it's everything. So.
Yeah.
Okay, thank you very much. Let's move to the last talk of the session, which is a simple dynamization of trapezoidal point location in planar subdivisions. And Martin is going to be giving the talk, and the authors are a group of 4 people from Sydney.
Hello.
Hello.
Let me see whether sharing that screen works. So, can you see my screen?
Yes.
Yeah, that's a good start. You can hear me, you can see my screen. Excellent. Okay, well, thank you very much for the introduction and welcome to a simple dynamization of trapezoidal point location in planar subdivisions. Our project started out as an undergraduate research internship here at the University of Sydney. And this is joint work with Nicolas, with Milutin, with Andre, and that's me. And what is point location? With point location, we mean the problem given a set of segments S in the plane, find the segment that is directly above a query point. This is also known as vertical ray-shooting queries. To answer many queries, it's lucrative to pre-compute a data structure. Structures for static sets are well understood and have numerous applications, for instance, in geospatial information systems for segment intersection reporting and other computational geometry problems. But how to perform efficient updates for fully dynamic sets is still not completely understood. So the basic question is, can one insert or delete a segment in such data structures without naive rebuilding? And in this paper, we show an extension of static approaches based on randomized structures. And we show how to extend these approaches to online, fully dynamic settings. The algorithms are very simple, thereby practical, and also work for intersecting segments. Our proofs currently assume non-crossing segments, for instance, edges from planar subdivisions. And the paper shows that updates take expected logarithmic time for the trapezoidal search DAG structure and expected log square for the trapezoidal search tree structure. So that's the overview of the paper.
Okay, are there any questions? Let me just ask the obvious thing. So therefore, when you have these two separate structures, you can't maintain them independently. I mean, meaning it takes log squared to update everything.
It's two totally different structures that are in nature very closely related. So the trapezoidal search tree has its own benefits, but the more commonly known structure is probably the trapezoidal search DAG, because the trapezoidal search DAG has expected linear size, and the trapezoidal search tree is slightly larger. It has expected n log n size. So it's two different structures. We show how to maintain either of them, and our best update times are for the trapezoidal search DAG.
Yeah, because your structure looks like it's a fairly straightforward dynamization of the randomized incremental approach.
Exactly.
And it's a fantastic runtime, and no one has done this in years. I was wondering, was there some particular hard step there, or?
Yeah, that is a good question. So maybe I should tell a little on the history of this problem.
It's been an open problem for a very long time.
Yes, so people were looking on point location for a long time and have many successful approaches on that. But one is still looking for sort of an holy grail structure for the online fully dynamic setting. The holy grail has linear size, logarithmic costs for queries, insertion and deletion operations, where each is deterministic worst case. And there are basically two conceptually different approaches. The one approach, the earliest approach, is based on trapezoids and the randomized incremental construction, and they're mainly providing offline structures. So the randomized incremental construction permutes input segments uniformly at random and inserts them one at a time under that order. And there are basically two different approaches in that regime. The one that is known as conflict lists plus walk for the search that identifies those things in the structure that need to be changed. And the other big approach was the point location plus walk approach. And in '88, Mulmuley showed that one can get an for the static problem, a structure of expected linear space and expected logarithmic query time with with either of these search strategies, but all based on the idea to do a point location search and a walk in the structure. Then it was Raimund Seidel who simplified the analysis a lot and made it much more understandable with his idea of backward analysis. And then in the early 90s, people also studied how to dynamize these structures. And there are several attempts to that. And first it was considered to do lazy deletions or non-lazy deletions. And there are two conceptually different approaches to that. The one dynamization approach is called dynamic sampling. That bases on the search idea of conflict lists and walks. And the other dynamization approach is called dynamic shuffling, which bases on the point location plus walk idea. And in dynamic shuffling, one uses some sort of rotations in the search structure. However, the analysis for these dynamization methods either requires that the whole set S is known in advance, so it's an offline structure, or that the update sequence is from a certain distribution of updates, and normally calls them the communist model. In the communist model, a deletion has to delete one of the segments that is currently in the structure uniformly at random, and every insertion needs to insert one of the segments that is currently not in the structure uniformly at random. So they only give bounds for update sequences that are from this distribution. So therefore, they're either offline structures or assume a very particular update model. Therefore, people started to look more at the segment trees approach, which provides online and fully dynamic structures. The first successful attempts were from Baumgarten, Jung, and Mehlhorn. They introduced dynamic fractional cascading to obtain a search structure of linear space. This was later improved by Arge, Brodal, and Georgidis with raising the fan out of the search tree nodes to improve the query time down to logarithmic. Then in 2015, Chan and Nekrich improved the segment tree approach further and either obtained linear space logarithmic query time, but updates above logarithmic, or they obtained logarithmic updates, but a query time that is above logarithmic. And combining their approaches with the best of the computational models, they achieve linear space and queries and updates that are slightly above log cardinality of S. And what our approach does is conceptually a little more back to the roots. So we focus on the randomized incremental approach, but our approach decouples the problem in two separate things. The first thing is the dynamization of a priority order, and the second thing is the structure maintenance. For the dynamic order maintenance, we use an arithmetic coding scheme on creeps, which gives us order comparison in expected constant time and updates in expected logarithmic time. And for the problem of structure maintenance, we introduce a new segment search. And this is now conceptually very different from how searches were done in the randomized incremental construction. And the other thing is that we do is we use recursive primitives. And yes, so our algorithms are very simple, but it's not so obvious how to analyze them. And to analyze them, we actually had, on a very abstract level, to combine ideas from backward analysis, but now on the permutation space. And the other abstract idea that we used was a sort of a conflict list analysis that was more, that used to be only applied for the conflict list approach. But these are like the building blocks of our runtime guarantees.
Okay, thank you very much. As we have time for one more short question before the break, if there are any.
I mean, I have one question, I guess. So, I mean, I guess all of this is still also for connected planar subdivisions, because for disconnected subdivisions, there's this additional issue of maintaining holes. Do you have any idea of how to, if your approach is more suitable to deal with this issue than the other methods?
Yes, that is an interesting question. Thank you. Yes, we only talk about vertical ray shooting. There are several things that one needs to do to also make it work for the general question where one wants to know the phase in which the query point is. It is not totally trivial to do that, but the nice thing is this structure allows to, yeah, no, I don't want to promise too much. It's not obvious how to do that in planar subdivisions that are not connected. Yes.
Okay, thank you very much. I believe that concludes this session. We have about 30 minutes for a coffee and cookie break before we reconvene for the invited talk of Virginia Williams, who is an excellent speaker, and I very much recommend that you come see it. Okay, thank you very much.